So here's kind of a neat application of geometric series. In this example, you're asked to write or use a geometric series to write the number 0.14 repeating as a ratio of two integers. So you may recall this notation here refers to the number 0.141414 with this pattern repeating forever. The goal is to use a geometric series. So the goal is to express this number as an infinite sum of the form a times r to the n. So to start out, I might break this up with 0.14 plus 0.0014 plus 0. Let's see, 1, 2, 3, 4, 0.000014. Okay, and I don't really care to continue much longer in that way. But the idea is to write this bit of this repeating decimal plus this bit here plus this bit here, with zeros filling in for what we've already expressed in the previous terms. Okay, so again, the target is to put it in this form. I'm going to write this 0.14 in the form 14 times 10 to the negative 2, right? And multiplying by 10 to the negative 2 would move the decimal over 2 places. So 14 times 10 to the negative 2 would give me 0.14. And then, so I'll write this number here as 14 times 10 to the, let's see, 1, 2, 3, 4, 10 to the negative 4. And then this number here would be 14 times 1, 2, 3, 4, 5, 6, so 10 to the negative 6. Okay, and then at that point maybe we feel pretty confident about the pattern. If I wrote one more term here, I would be scooching over 2 more decimal places, so I would have 10 to the negative 2 more in the next term in that sum. Okay, now again, I'm going to keep coming back to this. We want it written in this form. And, well, maybe we can do that right now. Let's see. So if I want to write this in the sigma notation, then I could certainly factor out 14. And then we have 10 to the negative 2n, looks like, right? With the sum, n goes from 1 to infinity. That'll give me 14 times 10 to the negative 2 when n equals 1, and then 14 times 10 to the negative 4 when n equals 2, and then 14 10 to the negative 6 when n equals 3, and so on. Okay, well, so this would equal the sum from 1 to infinity of 14 10 to the negative 2. So let me do a little scratch work here. So that's 1 over 10 to the positive 2n. And so that's 1 over 10 squared, which is 100, raised to the n. So this is our 10 to the negative 2n. 10 to the negative 2 is 1 over 100 raised to the n. So now we've got it in the form for a geometric series, where the first term, the a, well, let's not get into a right just yet, but our common ratio is 1 over 100, which absolute value of r then is less than 1, so this thing does converge. So that's a good sign. Okay, so let me replace this stuff up here with, now we've got it written in the form of a geometric series, the sum from 1 to infinity of 14 times 1 over 100 raised to the n. That's what I came up with down here. Okay, and we know it converges, so we want to find the sum. So the sum of that series is the first term. So remember, that's when you need to pay attention to where this sum actually starts. So it starts with n equals 1. So 14 times 1 over 100 to the first. So that's going to be 14 over 100 when you plug in n equals 1. Over 1 minus the common ratio, which is 1 over 100. So if I was going to simplify something like that, I would multiply the numerator and denominator by 100. Simplify the complex fraction there. So that way this cancels, so numerator becomes 14. Denominator, you have to distribute here. becomes 100 minus 1, because the 100s will cancel here. So 14 over 99. And I encourage you to put that into a calculator to verify, because it's a nice feeling of satisfaction to see that, yeah, when you put 14 over 99 into a calculator, you're going to get 0.14141414.